Hello everyone. So this video is going to be mainly an introduction and kind of like forward prep for a lot of what's about to come. So in this playlist, a major portion of it is gonna be us dealing with linear differential equations. So let me write that down. Linear differential equations, or DE for short. So question is, what are linear differential equations? What does being linear imply for a differential equation? And well, if I had to explain it as briefly as possible, there can be in the differential equation there can be no products of y and the derivatives of y with themselves or each other. Okay, let's actually write down a linear differential equation. So it looks something like this. Okay, so as I said, y. Okay, you can have the first derivative of y. Okay, you can have the second derivative of y. Yeah, this looks good, and so on and so forth. Like this, you could have up to the nth derivative. Okay, up to the nth derivative of y. So you have, suppose, say y and the nth derivative of it. Okay, so and basically what I said is, the y's and the derivatives of y, they cannot, these cannot be present as products of, of themselves, with themselves or each other. So suppose you cannot have a y squared here, that's not allowed. This y prime right here, you cannot have a y into y prime, that's not allowed. Y double prime, you cannot have this being squared or this being multiplied by y. All of that is not allowed. Okay, so kind of like these, anything concerning the dependent variable. Okay, all these terms of y and the derivatives of y, they cannot be involved with each other. Okay, the only thing that is possible is them being added with each other, and they can actually have coefficients. Okay, they can have coefficients, but the coefficients need to be functions of the independent variable only. So assuming that it's x. Okay, so suppose say y, it can only have a coefficient like, suppose say a, a naught of x. And the reason why I'm calling it a naught, y is actually just the zero derivative of y. That's why kind of ordering it like that. So basically, this can have a coefficient, but only as only a function of x. Okay, that's the only allowed type of coefficient. Again, same for all the rest. Okay, they can only have a coefficient as a function of x. Okay, so if y prime right here. Okay, so the coefficient of that again can only be a function of x. So we'll call that a1 of x. Y prime, again, the coefficient can only be a function of x, call that a sub 2 of x. And the same thing for all of them, all of the ones in between, and also the very last one, or it's actually in order here, it's actually in the first one here. Anyways, so a sub n of x, this is in fact a differential equation, so it has to equal something. And since we've dealt with all everything that's related to y, the only thing that you can have on the other side, okay, is actually just another function of x. Okay, so let's call that f of x. So this is how a linear differential equation looks. This is a linear differential equation, and in particular, assuming that your let's see, assuming that a sub n of x, okay, is not equal to 0, this is an nth order. This is an nth order linear DE. This is an nth order linear differential equation, and that's pretty obvious because the highest derivative is the nth derivative. Okay, this restriction is there just for the fact that we cannot have this disappearing if we are to call this the nth order differential equation. All right, so kind of like I think you've seen this before, with the quadratic formula and all, where you assumed a is not equal to 0, just because of the fact that it's a quadratic. So your x squared term cannot disappear. Anyways, enough about that. So, and there, I'd like to at least say something now, is that linear differential equations are much easier to deal with than the non-linear differential equations, at least usually. So with that said and done, let's actually narrow things down just a bit. And this is again, we are going to talk a lot about linear differential equations, but there's a narrower class that we are also going to focus on a lot, and they are pretty important. So those are linear homogeneous differential equations. Okay, so they're definitely linear, as the name implies. They're definitely linear differential equations, but I'm adding another term. All right. So basically, what it implies for this equation, definitely, as I said, uh, going by the name, it's definitely a linear equation. So definitely has this form, but also the term homogeneous here implies that this right side of yours, or the your linear expression involving your dependent variable and its derivatives, okay, this thing right here, okay, can only be equal to 0, okay, or in other words, okay, saying it in a very simple way, is that your f of x can only equal 0. So for homogeneous equation, homogeneous linear equation, f of x is equal to 0. So your equation is gonna look like, it's definitely a linear equation, as I told you, but your right side is gonna be 0. So a sub n of x, y, n. Now I'll just write it as short as possible. So all of that, and you have your a sub 0 of x multiplied by y, okay, and this is gonna equal 0, okay. This has to equal 0 for it to be homogeneous. All right, about the homogeneous equation, there's actually a really important, really interesting property concerning these, and I'll actually write this down now, and I'll prove it in a bit. So if you have a linear homogeneous equation, it has a really neat property, and it's that, suppose say you have two solutions. Okay, so obviously differential equation, it's gonna have solution. It will have a general solution, but obviously a general solution, as I said, it can lead to an infinite number of solutions. So anyways, let's say it has two solutions. Okay, let's say it has two solutions, y equals f of x, okay, and another one, let's say another solution is y equals g of x. Okay, y equals g of x. All right, so if you have a linear homogeneous differential equation in your hands, you have one solution, y equals f of x, you have another solution, y equals g of x. Any linear combination of these two solutions, okay, any linear combination. So wait, any linear combination, I'll explain that term in a bit, okay. Any linear combination is also a solution, okay, is also a solution of your differential equation. The main thing to ask is, what is a linear combination here. A lot of you might have seen this in linear algebra and other places, but for functions, it's similar. Anyways, for functions, what it means is, so you have we have two functions here, okay, f of x and g of x. So linear combination of these two are gonna be, so let's write down f of x, let's write down g of x. Now, a linear combination of these two is, in general, you can multiply any constant with f of x, any arbitrary constant, okay, let's call that c1. Multiply any arbitrary anything, okay, it can even be 0, it can be pi, it can be something negative, it doesn't matter, any arbitrary constant with g of x also. So let's call that c2, and any, you can also take the sum of these two. You can take the sum of these two, and this is basically a general linear combination. This is basically a valid linear combination of the two functions f of x and g of x, okay. So, and this theorem, okay, this is a linear combination, and what I just said here, okay, this theorem basically says that provided these two are solutions, okay, I'm assuming that these two are solutions to my differential equation, my linear homogeneous differential equation. All right, that implies that this right here, this linear combination right here, also has to be a solution, to my differential equation. That's actually pretty neat, and we're gonna use this fact a lot in upcoming videos. But before that, let's actually try to prove this. So first thing, what I'd like to see is, I said, I assumed that f of x and g of x are solutions. Okay, I can at least do that. So what does being a solution to my differential equation mean? All right. So let's actually look at something. So if f of x is a solution, let's actually try to write down the derivatives of that. So we have y equals f of x, y equals f of x. What's actually let's actually just omit the brackets and x for now, just to make things a bit shorter. So this is y, it's y prime, the first derivative, that's obviously gonna be f y double prime is obviously gonna be f double. I think you see where this is going. The up to the nth derivative, it's gonna look, the nth derivative of y is gonna be just the nth derivative of f, right? So, with that done, let's actually, I said that this is f is a solution of f of x is a solution of this differential equation. So I can plug f of x in here, f of x and its derivatives and all, and this equation is gonna be satisfied, right? This is gonna be a true equation, right? This is gonna be satisfied. All right. So what I'm gonna have, I think I can see already. Basically, if I just plug these in, instead of y, I'm gonna have f prime and all that until the nth derivative of f. So this is gonna be a true equation. This is gonna be true that let's see, we have a sub n of x, and that's multiplied with the nth derivative of y, or it's same as the nth derivative of f. So nth derivative of f, and it's gonna go on like that. So you have n minus 1 x and minus 1th derivative and all that stuff. So basically it goes on until you have your 0th derivative of just f itself. Okay, so a sub a naught of x multiplied by f, this is going to equal 0. As I said, this has to be true because f of x is a solution to our linear homogeneous differential equation right here. Okay, so I think this should make sense, but g is also a solution, so the same thing will apply to g. So this is true, this statement is true, and same thing is going to apply to g. So I'll just quickly write that down. So gn plus I'll all that and you have your plus right here, and the zeroth derivative, or just g itself. Okay, so this is also going to be true. Okay, for g, the g also satisfies this equation right here. All right, so if those are true, okay, I'll actually now try something. Is this going to be a solution? Is any linear combination that I form of f and g, okay, so this sort of expression, is this gonna, if I substitute this into the equation, is this gonna give me 0? Okay, let's verify if that is so. So first thing, if y is this, if we take y as this, what's the first derivative? What's the first derivative? It's obviously with all our addition, since we're differentiating the sum of two things, and also multiplying by constant, you can take the constant outside when you're differentiating, all that. The first derivative is gonna look something like this. So the only thing is you're just gonna have the derivatives of the function instead of the functions themselves. Okay, so just basic differential calculus, and this is gonna continue until the nth derivative. Okay, I think you see where this is going. So this is gonna continue until the nth derivative. The nth derivative is gonna look something like this. Just replace f and g by their nth derivatives right here. All right, and let's substitute all this into our linear homogeneous differential equation. If we do that, what we get here is, let's see, we have let's see, a sub n. Actually, yeah, I guess I would I should omit the x for now, but just remember that these aren't necessarily constants. Okay, they're functions of x. All right, anyways, so you have a sub n of x, and you have the nth derivative of y. So basically something like this, c1, and this is gonna continue until I'll write a few terms actually. So let's see. For the first derivative, it's gonna look something like this. Okay, it's gonna look something like this. C2, not f. And the zero derivative is gonna look some zero c2 f plus, oops, not c2, c1 f plus c2 g. Are we trying to prove that this is gonna equal zero? If it does equal zero, that means it satisfies our equation. Okay, so the way I should write it is, this is our left hand side, right? This is our left hand side. Let's see if it equals the right hand side. If it does, I think I showed it in a previous video. If you can verify that the left hand side equals the right hand side, just like any algebraic equation, this is going to mean that this is true and this is indeed a solution. So anyways, this is going to equal. Now what I want to do is actually separate the f, all the terms that have f in them and the derivatives and all, and separate them from the g's, all the g's. Okay, so if I do that, the thing is, okay, so you can just see from here, it's gonna be all these terms. Okay, f, it's all these terms. Okay, it's all these terms. All right, and one interesting thing, you can actually factor out c1 if you're taking all of if you're just taking all of these terms, all of them have c1 in them, as factors. They're all gonna be added. Okay, all of these terms are added to each other, so you can actually factor out c1. So it's gonna look something like this. This is gonna look something like this. If I just take the f terms, I can factor out c1. But what I'm gonna have is an n derivative of f plus all the things in the middle, all the derivatives and all in the middle, plus actually let's do this right. F prime plus a not just f. Okay. And the same thing with g. I'm gonna do the same thing with g. So let's if I just separate the g's, okay, the only we have done group the f terms, and now we're going to group the g terms. If I do that, same thing here we can take a factor of c2 out of all of them. All of these are added to each other, and we can take a factor of c2 out of all of them. So this is going to look something like c2 an and derivative, whoops, not f, nth derivative of g plus all of that in the middle plus a sub 1 g prime plus a not g. All right, now there's something really interesting happening here. Well, what is this expression? What is this expression right here? Okay, this is actually this expression right here. We actually wrote that a while ago. This is actually this expression right here, right? I just omitted the x's, but that's all really. It's just to really make it more concise. But this is exactly the same as this expression right here. And what did you say? Given that f is a solution to a differential equation, this has to be equal to 0. We know the value of that expression. This has to be equal to 0. So this expression right here, this long expression right here, the value of that is 0. And the same thing is going to happen here. We also wrote that since g is a solution, same thing with that. This expression is also, the value of that is also 0. That is also 0, as we can see. So the same thing here, same thing with g, um this is gonna be equal to 0. This is gonna be equal to 0. So all you have is c1 multiplied by 0 plus c2 multiplied by 0. This is gonna equal 0, which is your right hand side of your differential equation, since your left hand side equals your right hand side, this means your equation is valid. And this function right here, this test function right here, which is the linear combination of two known solutions, we know that this also has to be a solution. This must be a solution to our linear homogeneous differential equation. We have proven that fact. All right, it's pretty interesting. One last thing is that since we can actually have, as suppose say we have a third solution. Okay, third, suppose say y equals h of x is also a solution. You can do the same process with h, and then take the you can take the linear combination of all three functions. Okay, so this is gonna be c3 h of x plus c3 h of x, and you can repeat that proof, and you're also gonna get the same verification and all. This is again gonna be a solution. Okay, provided all those three functions are solutions of the differential equation, this is still gonna be a solution. So I think you can see where I'm going. What I'm trying to say is, in general, no matter how many solutions, okay, if you have a bunch of known solutions, any linear combination of those solutions is also going to be a solution. Okay, any linear combination, I actually add to here. Okay, add to the statement, any linear combination of solutions. Okay, no matter how many there are. Okay, as long as we know that they're solutions, any linear combination of them is also going to be a solution. It's pretty fascinating. Okay, and just one last thing, we have discussed what's a linear differential equation. We narrowed it down a bit, and now we're talking about what's a linear homogeneous differential equation, and we're gonna work with these a lot. And also for the next few videos, we're gonna actually narrow this down even more. Okay, so the types of equations we are gonna deal with the next few videos are linear linear homogeneous differential equations. So that much is true. uh, but again, we are gonna actually even narrow this down even more. Okay, linear homogeneous differential equations with constant coefficients with constant coefficients, and I'll write that down. So constant coefficients. So you might wonder, what does that mean? Actually, it's really just what the name implies. As I said, it has to be a linear homogeneous differential equation, as you can see here, going by the name. And the constant coefficient part basically just says that these coefficients of the derivatives of y. Okay, these functions of x, they are actually constants. Okay, they are actually just constants. So what it's gonna look like is something like this. So now it's gonna be a sub n, and actually, yeah, I'll emphasize that this is a constant. Okay, this is a constant, like something like 5 or pi or something like that. Okay, this cannot be a function that varies or anything. It's just a constant. So some constant multiplied by your derivative, your nth derivative, some function, and then it's just goes on like that. All of your coefficients of y and its derivatives have to be constants. So this is the class of differential equations that we're gonna deal with the next few videos. And these are actually really fascinating. We can see some interesting properties with these and their solutions. So that's it for now. The next video, we're gonna start with trying to find the solutions of these equations. In particular, we're gonna deal with the simpler ones, second order actually, and we're gonna extend from there. All right, see you in the next video, and study smart.